Hello everyone and welcome to lecture number 2. Today I'd like to go over some basic summary of models using differential equations, and I'll talk about some general ideas with modeling using differential equations, as well as go over some specific examples from population growth, specifically the Malthus model and the Verhulst model of population growth. And I'm also going to talk about some first-order ordinary differential equations theory that you should hopefully be familiar with from your differential equations class, but just I'll review a little bit of it. So to start off, in general, the mathematical methods that we use from model to model are extremely varied and range from very simple to very advanced. But typically, when we're doing continuous problems and continuous modeling, it often involves finding an exact or approximate solution of some kind of differential equations. And a differential equation is an equation relating the derivatives of several unknown functions, the dependent variables, to the independent variables of the problem. And probably the most important thing to do is to study all of the different classifications and become very, very familiar with the classifications that differential equations fall into. A differential equation is said to be sometimes just for short, known as DE, is said to be linear if every dependent variable and its derivatives appear linearly in the differential equation. And likewise, a differential equation is nonlinear if this does not happen. So if at least one dependent variable or its derivatives appear nonlinearly. In the differential equation. In general, linear differential equations are easier to find solutions for, which is very, very nice, and easier to find both analytical solutions and numerical solutions. And nonlinear differential equations are much, much more difficult and more nuanced when it comes to solving for. So this generally applies to both analytical and numerical or computational simulations or solutions to our differential equations. Unfortunately, in applications, the best and most accurate models are typically nonlinear models. And I guess it's not really too unfortunate because it provides a very, very rich avenue for research and understanding of real physical problems. But when it comes to applications, the more realistic, more accurate models tend to be nonlinear models. which are much harder to solve for in general. So the first, I shouldn't say the first, the next main classification that we have is the classification between partial differential equations and ordinary differential equations. So we'll start by talking about partial differential equations. Or PDEs, as they're sometimes called. So PDEs are differential equations with more than one independent variable. So you have a number of different examples of partial differential equations. I'll start off with two very, very nice examples, both exemplifying the linearity and nonlinearity considerations we just talked about. So if u is a function, u is the dependent variable in all of the examples that I'm going to do, we can talk about the one-dimensional wave equation and obviously for more complicated scenarios it's going to become more complicated, but whenever someone talks about the one-dimensional wave equation, they're typically talking about this equation right here. And c here is called the velocity, or the speed of the wave, the traveling wave. And u is the dependent variable in this problem. This is the 1D wave equations. This is in 1D. And it governs disturbances that propagate with speed c along one spatial dimension as a function of time. So in this case, u is a function of both space and time. The dependent variable u is the disturbance, and it depends on time and on space. Likewise, we can actually derive the wave equation in any number of variables. The wave equation in 2D is the second partial derivative of e with respect to t equals the wave speed c squared times the second partial derivative of u with respect to x plus the second partial derivative of u with respect to y. In which case u, in this case, in 2D, is a function of x, y, and t. And lastly, we can talk about the wave equation in 3 dimensions, which is a function of 4 variables, t, x, y, and z, and it's saying that the second derivative of this function u, the wave propagation, or the wave disturbance, second time derivative is equal to the wave speed squared multiplied by the sum of the second partial derivative of the disturbance with respect to x, y, and z. So this is sometimes called the standard wave equation, where c is a constant, called the wave speed. This is a very, very nice kind of picture, either whether you look at it in 1D, 2D, or 3D, but this is a linear PDE. And that is unless c is not constant. C is something more complicated, like unless C is a function of u, ux, uy, uz, or ut. In which case it would not be a linear wave equation anymore, and it would be a much more complicated PDE. So the next example that I want to talk about is what's called the Kdv equation. It's abbreviated as the Kdv equation, but this stands for Korteweg-de Vries equation, and this is actually an equation that is a mathematical model of waves on a shallow water surface. The derivation of this equation is rather complicated, so I'm only going to write down the 1D version. Even that's kind of complicated, but this equation is the partial derivative of u with respect to t plus u times the partial derivative of u with respect to x plus the third derivative of u with respect to x equals 0. The Kdv equation is a very, very standard example of a nonlinear partial differential equation. And this is a good classifying like this is a great practice to get into and to understand. But specifically, the nonlinearity is this term right here, because you have a quadratic term where you have the solution multiplied by the derivative of the solution, partial derivative of the solution. So this is the nonlinearity in the Kdv equation. And you might not believe it, but this complicates things a lot, especially for PDEs. Even linear PDE theory takes a little bit of time to develop and to understand how to solve correctly linear PDEs. It's why there's a whole whole couple of courses on it, both undergraduate and graduate, on solving PDEs themselves. But even so, going from linear to nonlinear PDE is very, very, very difficult. But we'll see by the end of this course that we will be able to figure out how to solve the Kdv equation and similar types of equations through use of certain methods that we can develop in the course. But mainly, they're both technically types of wave equations. The typical wave equation is a linear wave equation, and the Kdv equation is like a modified kind of more general nonlinear wave equation, but this describes what's called Russell's solitary wave phenomena. And we will actually see in the class that it can be solved analytically. And the experiment by Russell was very, very interesting and exciting. If you look back on the history of how this equation was developed, but the solutions are actually what are called solitons, and we'll see soliton solutions. Now, generally, when we're making models, we don't just even get single PDEs, we get what are called systems of PDEs. So a system of PDEs is a system of such equations. So when you have multiple dependent variables and multiple independent variables, each of which are related to one another through a complicated system, in terms of the partial derivatives, you have a system of partial differential equations. Each one of these partial differential equations is an example of a single partial differential equation. So I'm not going to write down exactly the general form for a system. We will talk about it a little bit later on, but some examples of systems of PDEs include Maxwell's equations of electrodynamics, the equations that govern the propagation of light, and electromagnetic fields, the Navier-Stokes equations of fluid mechanics, which are extremely important from a computational standpoint. If you want to, say, solve for the fluid flow over an airplane wing, or fluid flow over a race car that you're modeling, or a boat, or many other very important applied phenomena, or even what are called the Euler equations of gas dynamics. These are all examples of nonlinear systems of PDEs, which are extremely important and are solving them in general in the full 3 dimensions of space plus time is very difficult, and is still an open problem for these scenarios. The Navier-Stokes equation is actually $1 million prize offered up by the Clay Mathematics Institute if you can prove or disprove the existence of such solutions in 3 dimensions of space plus time. So it's a very difficult problem to prove anything about these in general analytically. But a single PDE of this form, so single PDE of this form, and we can see this up here in these examples. Each one of these examples can be written as a function of the u and its derivatives, and possibly of all of the independent variables as well. So it's a multivariable function of these set equal to 0. So it's some function f. We do f of all of the independent variables. So f is a function of x1 and possibly all of the independent variables up to k if we have k independent variables. It's possibly a function of all of the derivatives of u with respect to x, where u is the solution. Up to xk, it's a function of the second derivatives. And this is including the mixed partial derivatives, the second mixed partial derivatives, all the way up to and including the second derivative of xk. So for these derivatives you have k total, these derivatives you'll have k squared total, because all of the second mixed partials. You can actually reduce that because of if you can prove that it's continuous of the second partial derivatives are continuous functions by Clairault's theorem, the mixed partials are going to be equal to one another. But the idea is that we have to continue this all the way up until we get to the highest order derivatives. So the nth order derivatives, partial derivatives of u with respect to x1, and then all of the possible combinations of all of the derivatives of all the variables. So as you see, in general, a general PDE can be a very complicated thing. But the idea is that in general it's a function like this, and solving it involves solving for a function u that satisfies this for every single point in every single one of the independent variables. So for every point in the domain. So the next classification that we can make is the order of the PDE, and you might be familiar with some of these classifications from a previous class. I just want to make sure that everyone is on the same page. So the order of a differential equation is the highest derivative order appearing in the differential equation. We go up and look at the wave equation. The wave equation is a second order equation. It's a second order equation because the highest derivative that appears in the wave equation is order 2. It's the highest partial derivative order that we end up taking in the wave equation. For the Kdv equation, it's an order 3, a third order partial differential equation, because the highest order of the derivative that appears in the equation is this third order derivative right here. So we will touch on PDEs in this course a little bit, but the course is really focused on developing models for ODEs and systems of ODEs, and applying those results to real-world modeling problems. So the next thing we should do is talk about ordinary differential equations. These are differential equations with one and only one independent variable. But I also want to include as a caveat here, also possibly many independent variables. Or many dependent variables, not independent variables. There we go. So this is the main classification between ordinary differential equations and partial differential equations. Ordinary differential equations are also classified as linear versus nonlinear, and they're also classified with order, the exact same definitions for partial differential equation. In general, a single ODE for a single dependent variable we'll call it y, takes the form f of t, comma y, comma y prime, comma y double prime, all the way up to the nth derivative of y is equal to 0. Where f here is a multivariable function of the independent variable t and of y and all of the possible derivatives of y up to some order n, in where we call y a solution. Y equals y of t is a solution if this equation is satisfied for all t in some interval or set I. So we have many good examples of ordinary differential equations, many of which you're probably familiar with from your differential equations class. But the idea here is that very often in models a single ODE is not good enough, or if you have a very high order single ODE, you can actually rewrite this as a system of first order differential equations to simplify, and this is one of the things that we'll talk about in the as we move along in the course. But what appears more commonly in applications is a system of ODE of this form. And this involves multiple dependent variables and one independent variable. So typically we have, we'll call the dependent variables, the unknowns, y1, y2, y3, up to YL. These are dependent variables. And just like before, because we're dealing with ODEs, we'll talk with the independent variable as t. There's nothing special with the t here that I'm using. T could very well be x or any other physical thing that we're talking about. It doesn't have to be time. But very often in applications it is time. But it's important to make that point. So if I have L unknowns, I'll expect to have possibly then L differential equations to solve for those unknown functions. Our F1 is a function, multivariable function of t, all of the dependent variables, and then all of the derivatives of all of the dependent variables as well. This goes all the way up to the nth order derivative of y. L or y1 through yl. And if I have L independent variables, I expect to have L ordinary differential equations that satisfy this. for this that could all potentially be different as well, but that have to be satisfied in order to solve for y1 through yl. This is the function f1 is some function of all of the dependent variables, the derivatives of the dependent variables, and the independent variable. Same thing for f2. And we have this all the way down to fl, where these f1 through fls could be varying very much in complexity. One could be linear, one could be nonlinear, but the idea here is that in order to solve a system of differential equations, where we are essentially solving for if we have L differential equations, or a system of L differential equations, solutions are of the form of functions of t. So we can solve for y1 of t, y2 of t, all the way up to yn of t, or yl of t. Where I'll call this a double star star. This is our system of differential equations are satisfied for all t in some interval I, say. So as we move through the course, we're going to see a lot of examples of interesting, non-trivial systems of ordinary differential equations, and we're going to figure out some clever methods of solving them, solving certain examples, but also in general how to do both qualitative and quantitative analysis on various systems of both nonlinear and linear ordinary differential equations. For linear systems, there's a very, very nice theory and very, very well-known theorem that allows us to figure out the solution under very, very many cases. But the case of nonlinear differential equations is a little bit more difficult and takes a little bit more consideration. And typically in applications, when we have a very complicated nonlinear model, we're going to not necessarily be able to solve for the exact solution, but we will be able to determine properties of a solution and understand how the solution is going to behave. So we'll start off with theory of first order ODEs. And the idea here is that a single first order ODE is the most basic differential equation that will appear in a model, and even these can be very complex sometimes, so we have to be very careful. But a single first order ODE for y for a function y can be written as some function f of t, y prime is equal to 0 for all t in some set. If we can solve for a solution is of the form as we can be written as a function y of t, and this equation will have to be satisfied for every single t in the interval. Now, the theory in the book, in much of the ODE theory, involves rewriting this a little bit. It's solving for y prime. So y prime is equal to some function lowercase f of t comma y. And as long as you do it carefully, this can be done to great effect very often, and gives us a slightly more nice way of looking at solutions to this. So we'll call this equation 1. So, like, for example, I'm talking about the differential equation y double prime plus, or I'll say y prime minus r times y equals 0. We can rewrite this as y prime is equal to r times y. And this puts it in form 1, takes it from form star and puts it into form 1. Now, solving for y prime might not always be that easy, but the idea is that this is kind of the example here. And this is what the theorems are going to be placed on the function f in terms of our existence and our uniqueness theorem. So in this class, and we'll see examples where this is violated, but for the theory, our existence theorems depend on certain assumptions on this function lowercase f. So for the theory side in our book, we will consider such ODEs. Where f is a function from some interval in t, so a comma b, and y can range from c to d, and it's a function, multivariable function. So this is the set our t can range in, and this is the set that y can range in, where a, b, and c are all allowed to be possibly infinite values. So a is greater than or equal to negative infinity. It's strictly less than b, which is less than or equal to infinity. C is also satisfying in this interval, and D is also in this interval. And that's basically giving us a very wide range of possible ordinary differential equations that we can study. We can study differential equations that are population models, like we're seeing, that start at 0 and go to infinite time, and possibly have a population that's bounded by some maximum population. This is the solution axis. The population could look like this. Maybe the population goes up, decreases, and then goes up again. But this gives us a very wide range of possibilities. And we're also going to assume that at a minimum, f is a continuous multivariable function. Specifically, it's a function of two variables, t and y. And we define function y of t to be a solution of the ODE on an interval I which is a subset of AB, provided that the solution y of t stays between C and D, and y of t is continuously differentiable. For t in I. And we need this continuously differentiable in order for this equation to make sense. There are other ways of defining solutions to equations of this type, but they're much more advanced. It involves what's called the weak derivative, and you can actually define more generalized solutions to equations of both these forms. But it goes to a much more advanced mathematical level of sophistication, so we'll be sticking with the theory in the book, which is the classical theory of differential equations. And what defines y of t as a solution is that the derivative of y of t is equal to this function lowercase f of t comma y of t for all t and I. So the derivative of y is equal to the multivariable function of t comma y of t at any point t in the interval. Now, for a given differential equation, you have many possible solutions, because when you solve it, you'll end up having some sort of integration constant. So what we need to do is discuss what's called an initial value problem. And an initial value problem essentially is the problem of determining that constant of integration. We abbreviate this as IVP. So an initial value problem solves in ODE while specifying that it attains or hits some initial value. And this is some point t naught y naught in the set. It's an element of the set. The rectangle from A to B and C to D. And just for abbreviation in the future, we'll call this set D. It's a two-dimensional rectangle. And we see that Y solves the IVP if it solves the differential equation. It solves this differential equation right here, or 1. And that means that y prime equals f of t comma y on I, and it satisfies the initial condition, which is that y of t naught is equal to y naught, which is the initial value of the problem. So the first big theorem that we have, that it is proved in the book, but it's not proved until chapter 8 in the book. So if you want to see this, you can jump ahead, but we won't be going over this in the class. because this would be a different class where you would discuss this and learn about the proof of this theorem. But it is important to write down just to get an idea of what we're working with for the mathematical theory of initial value problems in general. So the theorem is that if a function from a domain like is described above to R is continuous, then the IVP with the solution should say a solution to the initial value problem exists with some maximal interval of existence. We'll call that alpha comma omega. This is an interval of existence that in general is a subset of AB. And this means the initial value has to be included in this interval of existence. So we can actually prove qualitatively some results about the solution. If alpha is strictly greater than a, so it's not equal to the boundary point a, then as we approach that boundary point, so as we approach alpha, the left boundary point is the limit as we go to the left boundary point. The limit of our solution has to be equal to C, our upper boundary for y, or the limit as t goes to alpha from the right of our solution has to equal d. And we can also say qualitatively that if omega, the upper limit to our interval of existence, is less than b, then the limit as t goes to that upper value from the left is going to be equal to c, or it'll be equal to d. This is just what this theorem is definitively saying about solutions to our differential equation. Now, like I said, we're not going to prove this, but we will use this, and we will state later on in the course some similar theorems for systems. But this gives us a lot of power. In addition, right, we can also have from this theorem, it's even more powerful if this function f is continuous. So if in addition the partial derivative of f with respect to the dependent variable, so with respect to y, or df dy for short, is continuous, then the solution is unique. And this is a big thing in mathematics. Investigating existence and uniqueness of a given solution. This theorem guarantees a maximal interval of existence for certain classes of ordinary differential equations, and we'll see that similar theorems can be found for systems. We won't go over the proofs of these theorems in this class, but it is important to consider for a given model. Do solutions exist, and are they unique? And some good examples applying this theorem can be found in the Kelly book. So I recommend looking in the Kelly book and looking at example 1.4 and example 1.5. Example 1.4 shows an example where the partial derivative of the f with respect to the dependent variable is not continuous, and therefore this example 1.4, the solution is not necessarily unique from this theorem. In example 1.5, it gives a slightly more complicated equation, but that does have a continuous partial derivative df dy. So in example 1.5, this theorem tells us that a solution exists and it's unique. And so a class of ODEs that you might be familiar with is first order linear ODEs. This is typically the first type of ODE that you see in basic differential equations class. And this will be the focus of today's lecture. We'll be doing population models with first order linear ODEs. And we'll also see how to do some population models with first order nonlinear ODEs as well. We'll kind of compare and contrast the two. But first order linear ODE is an ODE where your f function takes the form of a function of t times y plus some other function of t. This is the general form of f for first order linear ODE. And we can always get the solution to this as long as p and q are nice enough functions. So we're actually guaranteed a solution to this if p is a continuous function and q are continuous functions. And it's not typical for ODEs, but for first order linear ODEs, we have a very nice expression for this solution. The solution is y of t is equal to the initial condition y naught times the exponential e to the integral from t naught to t of the function p plus e to the integral of p from t naught to t times the integral from t naught to t of e to the negative integral from t naught to t. I'll do s naught to s actually, because we have a different t naught to s here of p of s, or p of tau d tau times q of s ds. So for any first order linear ODE, as long as p and q are continuous functions, this is the solution. So I do want to briefly go over the proof of this because it is worthwhile to talk about. And the idea here is that under the assumptions given, we can immediately apply our theorem from before. So f of t comma y is continuous because f of t comma y is just p of t comma y, or p of t times y plus q of t partial derivative of f with respect to y is equal to p of t, which is also continuous by assumption, so by our previous theorem, the solution to our initial value problem, the first order linear initial value problem, exists and is unique. And the next step to do here is to verify that the solution is in fact, the formula given right here is in fact a true solution to the differential equation, and that can be done by differentiating this entire thing with respect to t. You have to be careful here. You have that y prime of t is the derivative of this first expression with respect to t, and the derivative of an exponential by the chain rule is going to be the exponential times the derivative of what's in the exponential, which we have a definite integral in that exponential. The derivative of a definite integral with respect to t is just going to be this function, the integrand, as a function of t. So by the chain rule, then, this is going to be equal to y naught times p of t e to the integral from t naught to t of p of tau d tau. And then we have to add to this the derivative of this term right here, which is a little bit more complicated to write down. The first thing, derivative rule, when we take the derivative of this, that we're going to have to use is the product rule. And so this is going to be the derivative of this term, which is p of t times e to the integral t naught to t p of tau d tau times the integral from t naught to t of e to to the negative integral from t naught to t of p of tau d tau q of SDS. Oh, that should be s right there too. So it's the derivative of this expression right here times this plus now this, which is just itself times the derivative of this entire expression right here. Which is going to be e to the negative integral from t naught to t of p of tau d tau times q of t. And this is the product rule applied to this entire term right here. So at first this looks a little bit complicated, like we're not going to get the actual final solution of the differential equation, but sure enough, you notice here that you have an exponential times e to the negative of that same exponential. This is going to simplify to 1, and we can factor out a p of t from this first term right here to get p of t times y naught times e to the integral of p of t plus e to the integral of p of t times this integral right here and then lastly plus q of t, because this product simplifies to 1. And notice that this entire thing is the original solution for y that we started with, the original formula for y that we started with. So therefore, we have that y prime of t is equal to p of t times y of t plus q of t, and y therefore satisfies this differential equation. So there's a lot of very, very interesting problems that you can apply this to. Any linear first order ODE, you can use this formula to get the solution for. I recommend looking at example 1.7 in the Kelly book, which deals with a very interesting physical law called Newton's law of cooling that you'll hopefully be familiar with from your previous ODE course. Very successful and accurate model for a cooling object. So the modeling example that I want to talk about today is it's called population growth. And I think this is a great model to consider, especially considering what's going on in the world right now, with the idea of, say, modeling virus spread, the spread of a virus. or the spread of some population, which could be a wide variety of things. So in general, we talk about, we'll assume that P of t is some population or population density of some population at time t. This could be radioactive material or a chemical. Could be the number of cells in a cell colony. It could even be the spread of a virus, say. So a basic growth model is to assume that the rate of change in the population dp dt, or p prime for short, is exactly equal to some function, capital G, of time, so it's changing explicitly with respect to time, and it also maybe depends on the population value. So the rate of change in population is some function of time and the current population value. And the choice of G is going to give us exactly the type of population growth or decay, or the evolution of this population. And if G is a continuous function, by our previous theorem, we are guaranteed the existence of solution to any IVP that we pose. And furthermore, if the rate of change of G with respect to P is a continuous function, we are guaranteed a unique solution for the population growth. And the set that we're going to be considering this on is for t from 0 to infinity. And the population also could go to infinity, 0 to infinity. But it might go to some finite value as well, so it might just go from 0 to some maximum value, d. So the simplest model here, I mean, I guess there are simpler models, but I'll say the most basic model is it's called the Malthus model. And this model is to take G of t comma p to not depend on time at all, and to just be a function of the current population, specifically r times p, where r is some rate. And this gives us the differential equation, p prime is equal to r times p, which should be familiar. You should recognize this as the exponential growth model. When you go through and solve this, this is what's called a separable differential equation, which is one of your classifications from your previous ODEs course for first order ODEs. You can go through and integrate this and solve for p. You get that p of t is equal to the initial population times e to the r times t, where r is the growth rate. So r is sometimes termed the growth or decay rate. Because if r is positive, then you have exponential growth, and if r is negative, then you have exponential decay. So in your ODEs class, hopefully you saw examples of radioactive decay, Newton's law of cooling. Also is very, very closely related to this. The Malthus growth model. It's a little bit of a change in this function, g. But this is our most basic model of growth using this type of a growth model. You'll also notice that when you classify this classifies as a linear first order separable differential equation, ODE. So the solutions are relatively straightforward to go through and solve this. Now, as nice as this model is for certain things like radioactive decay, in terms of a growth model, and just in general, this solution in this model with a constant r has some limitations, and some of them are rather severe. One of the big limitations is that r, the rate, could depend on time. In which case, we can still go through and solve it. It still would be a separable ODE. It would just now depend on r as a function of t. So in order to solve it, you'd have to go through and use the previous formula that we talked about. This formula, by the way, is sometimes called the variation of constants formula for the solution of y. A bigger limitation, a much further limitation, is that r could also depend on p as well. It could also depend on both. And this is a pretty big limitation, because if it depends on p, if r is a function of p, well, then we'd have to guarantee that the derivative of this with respect to p, this entire thing, gives us a continuous derivative with respect to p in order to be guaranteed continuous, or in order to be guaranteed unique, and solutions that are unique and exist and are unique. And even if we assume r is constant, this model still has problems. It doesn't factor in the maximum carrying capacity for the medium. any growth problem or population growth is going to be have a maximum carrying capacity. And this is an issue. We'll call the maximum carrying capacity maybe M. See, it's capital M is the maximum carrying capacity of the medium. So the question here is, what do we do about this? How do we change the problem to just factor in this maximum carrying capacity? And the answer here was found by Verhulst almost a century later. And to do this, we choose a slightly different G. So we take the function G of t comma p to be equal to R, the growth rate, times p times 1 minus p over m, which gives us the differential equation dp dt, or p prime, is equal to r times p times 1 minus p over m. And big question is, why does this factor in the maximum growth rate? Well, when p is approximately 0, that means that p prime is approximately, well, it's r times p times 1 minus p over m, and p over m is a very small number when p is approximately 0, so p prime is approximately equal to r times p. So for small values of the population, we expect exponential growth. But when p is approximately equal to the maximum carrying capacity, p prime is approximately equal to 0. So as we get very close to the maximum carrying capacity, the rate of change of the population is approximately 0. So the idea here is we got to go through and solve this ordinary differential equation. And as it turns out, this is a separable ordinary differential equation, so we can go through and use separation of variables from our original ODEs class. Before we do that, though, and this is a very common thing that we'll be doing in the course and is a very useful thing to do, we want to learn how to do what's called non-dimensionalization. And I'll do it for this example problem to give you an example of what to do. The main idea here is that in step 6 of our procedure, when we write down our model, typically the variables that we write down are dimensional, and they have units. So the idea here is that when we do our mathematics and we do our numerical solutions, we don't really want to have to deal with these units and deal with making sure all of the units are being consistent and matching up. And we also want to learn, what terms and the scaling that we're, and the scaling and the scales that we're using, which terms are negligible and which terms are not negligible. So non-dimensionalization very often helps with this. So for this problem, in order to do that, we have to write down whatever the dimensions of P are. So we'll box P here and we'll say, write down the dimensions of P. the units of P could be cell density, virus density, population density, and this is going to have some sort of characteristic unit. And I think what we'll use is the maximum carrying capacity as the unit that we want to non-dimensionalize it for P. Likewise with T, to write down the dimensions of T. We're going to have units of time, so maybe seconds, minutes, hours, days, but for the characteristic time scale, we'll use R, because R has units of 1 over S. In order to keep this consistent, the dimensions here consistent, the units of P prime have to match up with the units of R times P. So R has to have units of 1 over seconds, or 1 over time. And what we'll choose as our characteristic length scale for time in this problem, we'll use R, the rate R. And if we do that, we can introduce new variables, which are dimensionless. This will be y is equal to P over M. P and M have the same units, so y is dimensionless. And we'll introduce tau, which is R times T. And tau is also dimensionless, because R has units of 1 over time, and T has units of time. And when we do this, we have to be a little bit careful with how our differential equation changes. Remember the initial differential equation, and this is for the general first order growth model. dp dt is going to be g of t comma p. Well, this becomes, by the chain rule, dp d tau times d tau dt, and this has to be equal to g of tau over r, because t is equal to tau over r, and we kept p the same. Now we plug in our form for p here, which p is, or y is p over m, so that means that p is equal to m times y. So this then becomes, when we plug this in here, we get the equation dt d tau dt is r, so we get m times r times dp d tau is equal to g of tau over r comma p, which is y times m. So finally, we have the expression, it's not dp d tau, I'm sorry, I made a little typo there, dy d tau. We have the differential equation dy d tau is equal to 1 over m times r times g of tau over r comma y times m. And this is a new ordinary differential equation, which is a dimensionless ordinary differential equation. So if we call this function right here, it's a function of lowercase f of t comma y, depends on the original function g as well as the scaling parameters that are kind of built into here, we get that dy d tau is equal to f of t comma y. And this is a non-dimensional ordinary differential equation. And for more advanced non-dimensionalization problems, this is a very, very powerful tool for us. But for relatively straightforward ODEs like the ones we have right now, the first order, this is still a very helpful tool because it simplifies the analysis. So remember, for Malthus, the Malthus, you have that g of t comma p is equal to r times p, which would mean that the differential equation for y with respect to tau, the non-dimensionalized differential equation, is going to be f of t comma y, which is 1 over m times r times g of tau over r comma y times m. So for the Malthus model, the non-dimensionalized differential equation becomes 1 over m times r times r times y times m. Which just simplifies to y. So it's dy d tau is equal to y, which is a much simpler differential equation to solve because you don't have to keep track of any units. You can just get the units after you solve the differential equation and plug in at the very end. So for instance, right, the solution to an ODE of this form is going to be that y is equal to y naught times e to the t, or e to the tau, and when you plug in, this is the non-dimensional solution. When you plug in the dimensional solution, this reduces to p is equal to p naught e to the rt. For the Verhulst equation, we get a slightly more complicated procedure because plugging in is a little bit more complicated, but I promise you that things work out really nicely. Because you have, for this equation, that g of t comma p is equal to r times p times 1 minus p over m. And therefore, f of tau comma y is going to be 1 over m times r times r times y m times 1 minus y m over m. So you get dy d tau is equal to, well, the m's here cancel out, the r's here cancel out, and you just have y times 1 minus y is the non-dimensionalized form of the Verhulst equation, which is, I would say, a much nicer differential equation to solve. in fact, you can go through and do that, and this is done in the book. And it does require a little bit of calculus, but the idea here is that this is a separable ODE, and I went through the solution in office hours. The main idea here being that you have to use partial fraction decomposition. So we're just going to rewrite this as 1 over y times 1 minus y times, and I'll use y dot as dy d tau. And if we integrate both sides with respect to tau, we get the integral of 1 over 1 minus y dot d tau is equal to the integral of 1 d tau. You can do partial fraction decomposition, which you'll hopefully remember from your previous course in ODEs, on this 1 over y times 1 minus y, to get that this is exactly equal to 1 over y plus 1 over 1 minus y. And this integral right here on the right hand side is going to just be tau plus c. So this gives us then that the general solution is going to be of the form natural log. When you integrate this, get natural log of the absolute value of y plus natural log of the absolute value of 1 minus y. Which, after applying some logarithmic simplifications, and oops, there should be a negative sign right here, you get that this is the same thing as natural log of y over 1 minus y or the absolute value of y over 1 minus y is equal to e to the tau plus c, which is the same thing as a constant a times e to the tau. Now, this expression right here is the solution to the ordinary differential equation, but it's what's called the implicit solution. And for some first order ODEs and higher order ODEs, you can find the implicit solution, but finding the explicit solution is not always that easy. But for this one it is. We just have to use our assumptions for the problem, specifically that the population is between P and the maximum carrying capacity, and this means that y is between 0 and 1, which mainly means that 1 minus y is positive. So y is positive and 1 minus y is positive, which means then we can actually get rid of the absolute value here to have y over 1 minus y is equal to a times e to the tau. And we can directly solve for this a. The a itself is given by plugging in tau equals 0 and figuring out this constant a. So at tau equals 0, y is going to be y naught, which means that a is equal to y naught over 1 minus y naught. And this also allows us to go through and solve for the explicit form of our solution, because if we take this and we rewrite it as y is equal to a e to the tau times 1 minus y, we can go through, and this is the same thing as y times 1 plus a e to the tau is equal to a e to the tau, which means that y is equal to a e to the tau over 1 plus a e to the tau. And this is the general explicit form of our solution, our non-dimensionalized solution. And when we plug in for a here, we plug in what we found for a, y naught over 1 minus y naught. This simplifies even further, and it simplifies down to y naught e to the tau over 1 plus y naught times e to the tau minus 1. Remember, this is the non-dimensional solution, which is important for letting our mathematics be relatively pain-free and smooth. But the idea is that once you have this explicit solution to the non-dimensional problem, you can always go back to the dimensional form of the problem at the very end, if that's what if you're interested in actual application, which is typically what we will be in this class. So when we plug in that y here is equal to p over m, and tau is equal to r times t, we can end up solving for p, and when we plug into this equation, we get that p is equal to m times p naught e to the r times t over m plus p naught times e to the r times t minus 1. And there you have it. This is the explicit solution to the dimensional problem. And if we open up a plot of this, I'm just going to use Desmos here to make a nice plot of the solution, we see something very, very nice. This solution is behaving exactly the way that we expect it to be behaving. This is a plot of the exact solution that we just derived. M times p naught e to the rt over m plus p naught e to the rt minus 1 for positive time t. And you see that in red here, it's a bold line. I've plotted the maximum population. We can change this around and see how the function changes when we change the parameter m, the maximum population capacity, the maximum carrying capacity. We can also see what changes as the growth rate changes. So if the growth rate becomes larger and larger and larger, you get a quicker jump. If the growth rate becomes very, very small, we get a more gradual change in the growth of this population. We can also even change the initial condition, right? If the initial population size is, say, 25, we have a curve that looks like this. But if it's much lower, around like 5, we have a curve that looks like this. And then if it's really small, we have a curve that starts off very small and then jumps up here. You can also go through and find the point where the concavity of this curve switches. So it switches from exponential growth to a decreasing growth as you approach the limit here. And a good exercise would be to go through and do that, right? Prove that this inflection point is m over 2. It's important to note that you can do this without solving the differential equation at all. If you take the differential equation itself, take the second derivative of it, and use that information, you can go through and show when this curve is going to have an inflection point. And this is an important idea, we'll be developing in the course, is taking a differential equation and without solving the differential equation, determining certain properties of the differential equation itself. But this is going to conclude the lecture for today. Thank you so much for tuning in. I hope you have a great day.